I'm going to change this. It says K. We've been using, it doesn't really matter what letters you use, but we've been using B and D, so let's just change that K and H to B and D, because that matches what we've been doing a little bit more. So this is C over B, and actually there should be a negative right there, and let's make that D.
There's another K in that you write about.
Oh, yep. Let's make that a B. There we go. If that doesn't bother you having those different letters, you don't have to change them. But we have been using A, B, C, and D, so if you need some consistency there, this is just reminding us what we're doing for these types of functions. So sinusoidal functions can be used, and that word sinusoidal, as we clarified the other day when we were doing that introduction, it sounds like it's talking about sine, but it's also talking about cosine. So it could be sine or cosine that we're talking about here. Now, if we use our calculator, it is going to give you a sine function. If you use the Desmos, you can do either one, sine or cosine. Some things that can be modeled by sinusoidal functions. It's basically anything that repeats itself over time. So, for example, the amount of daylight. Right now, our days are getting a little bit longer. And, yeah, we're getting there. And our days are getting a little bit longer. Is it June? It's in June, right? Whenever they'll be the longest. July. Yeah, time is going to change, which really doesn't have anything to do with the amount of daylight, but it'll make it feel like there's a lot more time. Is it July? Is it June 20th? Look at it. You looked it up there. See, there's some use to having everybody having a computer there. June 20th, he says, according to the internet. So you'll have your longest day then, and then the days will get shorter again, and then in December you have your shortest day. And so right now we have our days are getting a little bit longer. If you really think about that, it really does you can tell it sort of follows a sine curve, because whenever we get to the summer and we get to those long days, it doesn't seem like there's a lot of difference between like beginning of June and end of July, right? All the days seem pretty long. That's because on your sine function, you are at that top part of the sine function where you're right here, where it's really not changing that much. It's not very steep. Then, if you really pay attention, like probably in not too long from now, you're going to see the days are getting longer almost noticeably. Right? It seems like, we got a lot more daylight than we did back in December. And almost noticeably, it changes kind of quickly. Now, we do have daylight savings time in the middle of this part right here, which kind of changes your perception of it a little bit, because whenever daylight savings time happens, there's not actually any more daylight other than just a few minutes than the day before, but it seems like it because you're actually awake while it's daylight. So we do see that change, but we'll, if you think about it, it just barely increases and then decreases there, but then it's going to drop off a little more rapidly. So it does not follow a curve like this, where you get like an extra 20 minutes each day, and then they take away, it's not linear in that fashion. So it follows a sine curve. Ocean tides follow a sine curve. So you go to the beach, and you wake up in the morning and the tide's way far in, and then throughout the day you can literally watch it go back out, right? And they'll stay out for a while, and it also follows the sine curve. So if you pay attention to this, it seems like the tide's not moving. It seems like it's staying still for a while, and then you can watch it come in, and then it seems like it's staying still, but it's actually, depending on the weather affects it as well. But if you got pretty calm weather, it's actually getting just a tiny bit closer here, then it goes a tiny bit away, and then it goes out where you can actually notice it. Temperatures do this depending on where you're at. Certainly our temperatures do this because every year in the winter it gets cold, and then in the summer it gets hot, and then it gets cold again. So it doesn't fit a sine curve perfectly, because some years we have a little bit, well, like this year we've had a warm winter. We have not had that many really cold days, and we haven't had any snow yet, which I'm a little disappointed about. But we have a warm winter, but on average it kind of hits the sine curve. So anything like that repeats itself can be modeled with a sine curve. So they really have a lot of useful applications. And if we had some more time and I hadn't got the flu and missed the whole week and we've gotten behind on some stuff, I have a project that I've done with like ocean tides where we kind of make some predictions, and then you can go actually like 3 days later and check to see if your predictions were right. But I don't think we're going to have time for that project. So you have this table here. You don't have to look at the bottom of 387. I used to make kids write this down. So this is hours of daylight, and I can't remember it's from your textbook on 387. I can't remember where it was at, because where you're at would make a difference. You guys all know that if you're like in the northern parts of Alaska, it might be daylight all day long at times, and then dark all day long at times. So this is probably somewhere closer to the middle of the Earth, not Alaska here. But we see the daylight for each day. So I'm going to show you 2 ways to do it. Let's use Desmos first this time. So if you will pull up Desmos on that computer. And I don't think any of you have done this. Well, I'm pretty sure Coach Wood didn't know how to do this on Desmos last year, so I don't think any of you have done this on Desmos. I kind of like Desmos, the way that it does it. So if you click the plus sign up here in the corner and tell it to enter a table. And I'm going to have to move this over here so I can see both at the same time. Alright, so you're going to tell it to enter a table, and it's going to come up with this table x1, y1. So you're going to enter all of your x coordinates in the x1 list. So it's just going to be 1 through 12. In this list. And then you're going to enter the y's in y1. So 10.68, 11.3, 11.9, 12.77, 13.42, 13.75, 13.6, 13.05, 12.3. And one thing I like about this is, look, it's already graphing all those points as you type them in. Like on the calculator, you have to go to a separate window, and you got to have your stat plots on, and you got to do all of those things. So I'm gonna walk around and make sure everybody's able to get that to work for them. I think so. It looks like everybody's getting that to work. Okay. Any troubles? Everything working for everybody? You may have to change your zoom over here to see your graph depending on what your graph looks like. Okay, so to do a regression for this, so to do a sinusoidal regression, on Desmos, what you're going to do is you're going to type in, basically you're going to type in y equals a times sine bx plus c plus d. But instead of typing y, if you type y and just type a 1 right after it. So I didn't do anything but type in y and 1, and it automatically made it like that little subscript there. And instead of typing equals, I'm going to type the squiggle. I think so you're going to type the squiggle. The squiggle, if you do shift and the key up there beside of your 1, your squiggle should, or at least that's where it's at on my keyboard. I think it's on yours too. And then just type A, sine, parentheses, B. Instead of typing an X, I'm going to type an X1 plus C plus D. And it just shows up. I kind of think this is easier than using the calculator. But you do have to know what form you're typing that in. That's what makes it a little bit more difficult, is you do have to know that that's what you're typing in. We've got it all now, because if you look right here, it gives you the values for A, B, C, and D. It gives you the values for A, B, C, and D. Now, you will notice, look, over here, did it print on yours? It printed on yours. This is what I got in the calculator. Whenever I did it on the calculator, it is different than what I got when I did it over here. They put a negative A right here instead of a positive A, which means that the graph is going to start there at a minimum. Well, it's got a phase shift too, but it flips that graph upside down. So I don't know exactly why it does that, but it does. And then I also have a negative B, and I don't really know why they put that negative B there. But you can see the graph works, right? And so this because sine is periodic, your phase shift is different, but your midline is the same. And these two numbers are the same, they're just negative. So what's going to happen is this equation might look a little different than the one you get in your calculator, but it will still work to make any predictions from. So it will still give you what you need there. So this works. You could even and so from this, we'll use this to answer some of the questions here. Now, it's a little bit different than what we've got here, so let me do that. Oh, I can't look at both of these at the same time. Hold on. All right, so I'm just going to change this right here. You might want to change yours as well on the next page to be the function that we got here. So I'm just going to go with 3 decimal places. You could keep more if you want. We're going to run out of time on this one too. Let me write if I'm not in presentation mode. I hope. Don't do that. I want pins. Okay. Alright, so once I've got the equation, if I want to know the amplitude, I could do 2 pi divided by this number in front of my x, 2 pi over b, right? We're going to ignore that it's negative because I'm sorry, we're not for amplitude. I have to lose my mind. Okay, 1.598. Ignore the negative, right? Because amplitude's always positive, even if it's got a negative in front of it. Period, we're going to do 2 pi over 0.512. The Desmos, for some reason, gives you a negative right here, but your period also can never be negative, so ignore that negative right there. That's going to flip the graph over the y-axis, but you don't really even need to know that. You just need to know how to find the period. It's always positive. So you're going to do 2 pi divided by 5.12, which we can even do on Desmos. 2 pi divided by 0.512, and we get 12.272. Okay, right there. Our phase shift is our 7.886 over the 5.12. Oh, I think we need to pay attention to the negative this time. Because phase shift can definitely be negative. That would mean that it's going in the opposite direction. So it's going to be negative C, so 7.886 over negative 0.512. I think we need to include that there.
Yeah, ours is minus.
Do you guys have a plus sign right here with your C when you typed it in? Yeah, oh, your paper, yes, I changed mine. I changed mine to match my Desmos. Here, so that other one is the one you're going to get if you use the calculator. So I have changed mine to match my Desmos, so I'm using those numbers. If you had used the calculator, you might get a different phase shift. You'll get the same amplitude, period, and vertical shift in midline. The phase shift might be different, but as we're going to see in a moment, the phase shift really doesn't matter that much for these. So I changed mine to use the Desmos there. That's why it's different from what you've got there. So let's see if we do negative 7.886 divided by negative 0.512. Oh no, yep. Well, it put the negative in the bottom, but it still works, right? So you get 15.402 for our phase shift. It does give you a different phase shift than if you had used the other one. But what you will find if you look, I think, if you use the other one, I think it's going to be, like the other one gives you like 3 point something. And so it's like that phase shift plus a whole nother period. I don't know why Desmos does that, uses that bigger number. But it still works for the equation, so it really doesn't matter for us. And then our vertical shift is that up 12.116, so the midline would be at y equals 12.116. Okay, questions? I think we're going to stick with Desmos today, and you can use Desmos on the quiz part we'll take tomorrow, because everybody can use Desmos at home, and not everybody's got a graphing calculator. So I'll show you the graphing calculator eventually, and I think this is easier. So the amplitude was 1.598. What does that mean in the context of? Actually, I want to do number 2 first, and I want to do 2 and 3 before I do number 1. Number 2, the period of the graph is 12.27. What does this mean within the context of the problem? And when we say within the context of the problem, we need to remember that our x was months and our y was hours of daylight. So, what does the 12.27, the period that we found, tell us? It doesn't have to do with the day. Or it does have to do with repeating. So, how long does it take for it to start to repeat? 12.27 months. Because when you're looking at periods, you're looking at the x-axis, so it's going to be months and not the hours. The pattern repeats every 12.27 months. Now, knowing what we know about the way the world works, is 12.27 correct? What should it be? It should be exactly 12, right? However, these are from measurements that are taken, so if the measurements were a little bit off, if it was really cloudy one morning and the sun, you didn't see it come up quite as early or any of those things, then that would have thrown this off a little bit. So when we're taking experimental data and creating an equation, it might not match what we know to be true for the whole entire world, right? But if we were to take data, a lot more data, like we looked at the last 200 years instead of just this year, then you would probably see that get closer and closer to 12. It probably would be slightly more than 12, but I don't think it's as big as 0.27. I think it would be smaller than that because 4 years just makes up for 1 day, so I think it would be smaller. But you're right, it probably would be slightly above 12 for that. So we've got a midline at 12.116. What does this mean within context of the problem? Midline is y equals, what's our y stand for? It's hours of daylight, right? So that's the middle ground for hours of daylight, right? So this gives us the average amount of daylight. So your midline is sort of your equilibrium. It's your average. It's going to, as the sine function, it's going to go above that and it's going to go below that, but it's going to oscillate back and forth around that area. All right, so now if we say that's the average amount of daylight, what does the amplitude tell us if we go back to number 1? It doesn't give you the maximum because like the maximum would be 13 and the amplitude is 1.598. Yes. How far the maximum or minimum is from the average. Because that's what the midline is in the middle, and then the amplitude tells us how far we go up or down from that, right? So your maximum is 1.598 hours more than your average. So if we were looking at Alaska instead, what do you think would happen to that amplitude? Increase or decrease? If we're in Alaska, we're probably going to have some on there, or we've got like 23 hours of sunlight. But we're also probably going to have some time where we might only have 1 hour of sunlight. So the amplitude would increase because you got bigger fluctuations between the high and low. The midline would actually probably stay pretty close to the same because your average is still somewhere between there, but your amplitude would get a lot bigger if we were looking at Alaska here. Now, phase shift. We actually got a different phase shift when we did Desmos, but either way, 3.13 to the right or 15.4 to the right, it really doesn't matter because if you subtract that period, it's just adding an extra period to it. But phase shift, since we're running out of time, I'm going to just tell you, phase shift doesn't tell you anything except for it just lines up to the data. Okay, so phase shift just lets that line up to the correct data. Okay, so let's see, did I print the last one that has this assignment on it? 7, 8, 10, 11, 13, 15. Okay. All right, so tonight I want you to try those. There's only a couple of them that you actually have to do the regression. The other ones give you the equation. Tomorrow we will go over this extensively and ask questions on that homework because we didn't get to do our second example here. We will go over this and I'll give you plenty of time to ask questions. before we take that last part of the quiz. Okay, so if you're having a little trouble on the assignment, then you can ask questions about that before we have to take that quiz. And I do have tutoring if you're totally lost on something, or especially if you didn't do so well on today's part of the quiz. If you want to come ask some questions about that, I can help you, because it still involves the same stuff when you're answering questions on this. And if you haven't put the Desmos app on your phone, it works just like the one on the computer. It's so wonderful. I love it.